Hello and welcome to the Typhoon Hill microgrid testbed video. We're going to illustrate the features of the microgrid testbed on the example of a 13-bus microgrid with 4 different distributed energy resources. First, let us understand why use controller hardware in the loop for microgrid simulation. The precise definition of a microgrid is an open topic. While there are a lot of details in discussion like power range, 2 things are taken as granted: the presence of distributed energy resources and the capability of operating in both island and grid-connected mode. These 2 characteristics imply how complex and dynamic a microgrid is. With the advance of power electronics, the number and complexity of microgrids will only increase over time. So, in this highly dynamic environment, how do we efficiently test all of the controllers? Should we test the controllers in power labs? The answer is no. Power labs are expensive and lack the ability to safely test controllers in edge cases. Using the Typhoon Hill microgrid testbed, real microgrid controllers are connected to an emulated microgrid and have their behavior analyzed in real time with high fidelity for a full range of tests, and with no assumptions made on the control side. The control development and tuning are made easy, and fault response and interoperability can be precisely observed with a full automated test study. Now, let us go back to our example. The microgrid implemented is represented by this single line diagram. To simulate and test our controllers, we have a rack containing all the equipment used. All the power stage, or in other words, all that is represented by the single line diagram, is simulated in 3 Hill units. The power plant is a 3-feeder microgrid that operates at 13.8 kV and that is composed of dynamic and passive loads, transmission lines, transformers, relays, 2 diesel gensets of 1 and 4 MVA, and 2 photovoltaic inverters of 25 and 35 kW. The 4 MVA diesel genset, also called Gen 2, is controlled externally by a Woodward EasyGen 3000 controller. The 1 MVA genset, or Gen 1, is software controlled with control loops designed with the digital signal process blocks from our library. The 35 kW photovoltaic inverter is controlled by a firmware from Austrian Institute of Technology, or simply AIT, flashed in a TI Delfino board. The 25 kW PV inverter is controlled by a Hummingbird controller by Schneider. None of these controllers had any modifications in their structure to be connected to our Hill units. As the Woodward EasyGen 3000 and the Schneider Hummingbird controllers operate in different current and voltage levels than our Hill, a Hill Connect interface was created especially for them. This microgrid model runs at a time step of 2 microseconds in 3 new Hill 600 series connected in parallel. Now that we understand the microgrid model, let us take a better look into how we implemented its structure and controls with Typhoon Hill software. In our software, the single line diagram is implemented as a 3-phase diagram and built with elements directly from our library. The diesel gensets are implemented as synchronous machines that have voltage and speed controlled respectively by an exciter and a governor in the primary loop. In the exciter loop, the voltage from phase to neutral of the 3 phases are measured at the point of connection with the grid, and the equivalent terminal voltage is calculated. This voltage is then sent as a feedback to the exciter that compares with the defined reference and apply a field voltage that will bring the terminal voltage to its desired set point. In this case, we are using an IEEE DC1A exciter together with the PI controller. This IEEE exciter is available in our Power System Signal Processing library, along with other exciters such as AC1A, DC4B, and ST1A. If you want to use a different exciter that is not available in our library, you can use signal processing elements to build your own. In the governor loop, the speed is measured directly from the synchronous machine, compared to the reference set and sent to the governor and engine, which will output the torque needed to bring the machine to the desired speed. In this simulation, we implemented the DE-Gov governor from Woodward. Its dynamic behavior is represented by the electric control box and actuator transfer functions, while the engine dynamic is represented by a simple time delay. As with the exciters, we have IEEE governor and steam turbine elements available in our library. The inner control loops described up to now are the same for both Gen 1 and Gen 2. The difference between them starts with the secondary control loops. Gen 1 has two secondary control loops, one to control the generator real power output, called P loop, and other to control the generator reactive power, called Q loop. The Q loop measures the reactive power at the terminal of the machine and compares it to a reference set. This reference passes through a PI controller that outputs small deviations in voltage reference to the exciter. It is possible to disconnect this loop from the rest of the machine control by setting the Q control mode input as 0. The P loop is similar to the Q loop, but this loop measures real power at the machine terminal and applies small deviations in reference speed to the governor. This loop can be disconnected by setting P control mode to 0. With all these loops, the genset can be controlled in three modes: VF, in which the speed and voltage are precisely controlled. This mode is ideal for a standalone operation. PV, in which real power and voltage are controlled. As this control mode perturbs the reference speed, it can only be used to operate in grid connected. And PQ, in which real and reactive power are controlled. As the PV mode, this mode can only be used in grid connected operation. Gen 2 does not have the secondary loops implemented in our software, since the external Woodward EasyGen 3000 controller is the one responsible for that. In our schematic, we only have to use an externally controlled voltage source to receive the information sent by the controller and send small voltage deviations to the exciter. Another externally controlled voltage source is used to send small deviations in speed to the governor. The PV inverter are both three-phase, three-level inverters that use the maximum power point tracking algorithm known as MPPT. The PV inverter controllers receive information measured at the point of connection to the grid and send commands to the inverter block. In this block, you can define which channels will be used to receive commands. Dynamic loads are represented by constant power load elements from our library that can have their set points changed during simulation. Passive loads are represented by resistors, inductors, and capacitors. Long transmission lines are implemented with pi models with mutual inductance and capacitance, while short lines are just resistive and inductive with no coupling. The relays implemented are of the type SEL787 and have protection of instant and time over current, time under voltage, time over voltage, and synchronization check. The relays communicate via Modbus. One of the relay subsystems consists of the breaker that will receive commands from the proper relay subsystem connected above. To implement short circuits for fault analysis, we used single-phase contactors that, when closed, connect two phases together. We used an impedance in series with the contactors to regulate the level of the short circuit current. Once we complete the model with everything needed, we can compile and upload it in the Hill units by clicking one button. Now that the model is uploaded in the Hills, we can load the settings we previously saved. This settings file contains all information regarding the analog and digital outputs for each of the three Hill units: sources, PV curves, contactors, machines, power electronic switches, power loads, and other user-defined variables. Before starting the simulation, let us open our predefined custom user interface. This custom user interface is designed in a SCADA type view, where information of every bus can be viewed in real time close to the bus where it belongs. All the interface with the controllers, hardware and software, can be done through widgets from our library. Some of the constant power loads follow a predetermined profile that is set via macro widget. In this widget, we wrote a script using Typhoon Hill APIs to load the MATLAB file that contains all profile data. We load the profile and set the initial values of power in the onStart handler. As the name says, this handler will be executed when the simulation starts. Then, in the onTime handler, we set a loop that updates the real and reactive power of the power load with 1 point from the profile curve at each iteration. When the counter in the loop reaches its maximum value, it is set back to the initial point and the profile starts over. The time of execution between two iterations of the loop can be chosen from the drop-down list. For these profiles, we choose an execution rate of 1 second. A similar macro widget script was used to simulate the change of irradiance during some period. In this case, the profile was declared in the custom user initialization script as a global variable that can be read by any other widget used. Thus, we did not use the onStart handler. With the script in the onTimer handler, the irradiation setpoints are updated every quarter of a second. We also declared the illumination variable as global to be able to plot the profile with the tracegraph widget. We can now start our simulation. The simulation starts with the microgrid connected to the grid, while all the ERs are off. To connect the Genset 1, we need to start it disconnected from the grid until it ramps up its speed to nominal value. Once it synchronizes with the grid, we can close the contactor and change its control mode for PV. It will now regulate power and voltage at the bus it is connected. We can change the real power reference and see how it reacts instantaneously. The same startup process is automated by the Woodward controller for the Genset 2. To start the Woodward controller, we need to clear its alarm register, and if the grid is under nominal conditions, no alarms will appear and the Genset will start. We can observe the speed ramping up with the tracegraph widget. Once the speed reaches nominal state, the controller enters the synchronization mode. To observe this process, let us take a look into our scope. In the third viewport, we can see the waveforms respective to the Gen 2. The magenta sine wave is the phase A voltage at the Genset point of connection. The red and green sine waves are the voltage and current respectively at the Genset terminal. Once the current and voltage are in phase with the point of connection voltage, the Woodward sends command to close the contactors and connect to the grid. Once connected, it will ramp up the power to the set point defined. The AIT inverter starts producing power once it feels that the voltage and frequency levels are within the specified range it was developed to work. The Hummingbird inverter will only close its contactor under nominal grid operation and will start generating power a few seconds later. Now, all the ERs are connected. Different scenarios can be studied according to what the user desires. Changes in power reference, irradiation, contactor control, and device faults are only a few examples of what can be done in real time. In this video, two scenarios will be studied. In the first, we will cause short circuits and analyze the system response. In the second, we will check how our controllers behave under a low voltage ride-through test. For the first scenario, we implemented three types of short circuits. Two temporary, one with high impedance and one with low impedance, and a permanent high impedance phase-to-phase fault. To execute the temporary short circuits, we use the button widget that will close the contactor that ties two phases together and reopens the contactor 30 milliseconds later. To capture the event waveforms, we use our capture tool and set the trigger as the state of the short circuit contactor. Once it changes to closed, the system recognizes the trigger and captures all the waveforms set with the decimation and number of samples defined before. First, let us set the trigger for the low impedance short circuit contactor called SCR6. The impedance of this short circuit is of 0.9 ohms, and its expected current is of 11 kiloamps. Let us enable the trigger, cause the fault, and take a look at the waveforms captured. As expected, the short circuit current was around 11 kiloamps. This current is above the instant overcurrent limit IOC defined at the model initialization, and thus the relay is expected to trip instantaneously. Indeed, the relay 6 opened in less than 8 milliseconds after it crossed the IOC limit of 7 kiloamps. This time is less than 5 cycles, which is the maximum time required for a relay to open instantaneously. The Hummingbird inverter disconnected in about 12 milliseconds. That is slower than the Relay 6 reaction, but even though the short circuit was cleared, the inverter suffered a DC link over voltage and had to disconnect. The AIT inverter used in this model does not have a contactor control, thus it does not disconnect from the grid, but stop its operation. We can see that it stopped its operation in 50 milliseconds, also due to DC link over voltage. Both gensets supplied power to the short circuit. In this case, the short circuit was not enough to cause the Genset 2 protection to trip. Genset 1 did not have any problems either. Through this capture, we can see that the Gen 1 speed response is faster, but has higher amplitude oscillation. Now let us clear the Relay 6 register and allow it to reclose. Also, let us reconnect the DERs that tripped off. Our microgrid is back to its nominal operation. Let us set the trigger for the high impedance contactor called SCR7 and do a capture the same way we just did. This short circuit has an impedance of 4.5 ohms and thus its current is expected to be around 2.8 kiloamps. Let us enable the trigger and cause the fault. As we can see, the short circuit current matches the calculation. This level of current is above the defined time over current limit, TOC, but smaller than the time over current limit. This means that the relay cannot open instantaneously, but with a time relative to the current level. For this case, the relay should only open if the fault stands more than 0.96 seconds. As this is not the case, the relay should remain closed. And that is what happened. As we can see, the Hummingbird did not disconnect with this fault. The AIT inverter stopped operating for a few milliseconds and went back to nominal operation. The gensets had similar behavior to the first short circuit analyzed. Let us once again bring our microgrid back to nominal operation. The last short circuit case studied here is the high impedance permanent fault. The fault is the same as the last analyzed, but only with its duration increased. Let us enable the trigger and cause the fault. As the short circuit is permanent, the fault was cleared only by the protection relay 6 after 0.97 seconds, confirming that the relay is operating as desired. Genset 1 supplied power to the short circuit, but had oscillations in speed that also had an higher order harmonic disturbance. Genset 2 disconnected in about 0.11 seconds because of high voltage at its terminal. The Hummingbird disconnected from the grid right after the fault was cleared by the Relay 6. The reason for it disconnecting is the same as in the previous cases studied, DC link over voltage. The AIT inverter had an oscillatory behavior during the whole fault period. It could not maintain a satisfactory DC link voltage level but did not stop its operation. As a result, the currents injected in the grid were also distorted. Once the fault was cleared, all the distributed energy resources returned to their nominal operation. In the second scenario, we implemented two low voltage write-through tests by writing scripts inside the button widget. There are two types of LVRT implemented, a weak and a strong. The strong one is exactly the same curve as described in the BDEW guidelines, while the weak follows the same pattern but with smaller voltage dip levels. To execute the LVRT, we change the amplitude values of the three-phase voltage source that represent the stiff grid according to the profile desired. To help us capture the event in the moment it occurs, we set a variable called LVRT probe right before the fault and use it as a trigger to our capture. So let us enable the trigger and cause the weak LVRT. As we can see, only the Woodward controlled genset disconnected from the grid. The AIT inverter stopped its operation for 1.30 seconds during the time when the grid voltage was below 90% of its nominal value. When the voltage level reached 90%, the AIT started operating, but with similar behavior to what was seen in the last short circuit case. Once the voltage level returned to nominal, the AIT inverter also returned to nominal operation. The Hummingbird inverter rode well through the fault and did not disconnect. Both gensets had similar behavior as for the third short circuit studied. Let us enable the trigger again and cause the strong LVRT fault. In this case, the AIT inverter had the exact same response as in the previous case. The Hummingbird disconnected from the grid in about 50 milliseconds due to a variety of reasons, such as DC link imbalance and overvoltage and loss of PLL lock. Both gensets showed similar behaviors as in the previous LVRT. In conclusion, microgrids are becoming ubiquitous and the number of renewable energy resources included is increasing substantially. The response of multiple DERs with different dynamic behaviors to various types of faults becomes unprecedentedly important. High-fidelity real-time simulation with a real-time interface now becomes a critical tool for testing and developing microgrids controllers before using high power. We hope you enjoyed this video. Thank you for watching and make sure you subscribe to our YouTube channel for more videos.